Hello, dear students. We are back again with another video lesson for the grade physics for grade 10 students. Today's lesson, we are continuing solving the questions in practice 1A. If you remember, in the previous lesson, we stopped it here, sample problem 1A. And now we are going to solve all questions in practice 1A. Question 1 says, a human hair is approximately 50 micrometer in diameter. So the diameter of the human hair is equal to 50 micrometer. So express this diameter in meter. So we have to convert this micrometer to meter. If you remember in a previous lesson, we said that to convert large prefix to the small prefix, we have to use positive power, and convert small prefix to the large prefix or small quantity to the large quantity, we have to use the negative power. As we studied in a previous lesson, we had two different types of prefix, large prefix and small prefix. For the large prefix, we had giga, mega, kilo. Giga, it is power 10 power 9. Mega, it has a power 10 power 6. And kilo, power 10 power 3. So for the small prefixes, we had like centimeter, centi, it is value in power 10 power negative 2, milli 10 power negative 3, micro 10 power negative 6, and nano 10 power negative 9. But sometimes during converting, sometimes we have to use the positive power and negative power, okay? So when does the positive power can be used? If you are converting large to small. But in the case of small to large, we have to use the negative power. So it is very important for the students to know that which one is bigger and which one is smaller. Between micrometer and meter, which one is larger? Meter is larger than micrometer. Now, we are converting from small to what? To large. Converting small to large, we have to use the negative power, okay? So what is the dimension of this quantity? Diameter is meter, okay? We have meter, and bring down this 50 times, and small to large. We have to use positive power or negative power? Negative power. What is the negative power of micro? 10 power negative 6 times 10 power negative 6, and write down the last unit. What is the last unit here? Is meter. Okay? The final answer for this question is 50 times 10 power negative 6. And sometimes we can simplify this value. Okay? For example, if I bring in the multiple choices, you can simplify this number. How? Guys, this 50, we can simplify this 50 to what? To 5 times 10 power 1. 5 times 10 power 1 is equal to 50. There is no difference between these two numbers, okay? But we can express this number as a power. How can you convert this number to the power? 5, the 50 is equal to what? Look, 50 is equal to 5 times 10. 5 times 10 is equal to 50, yes. So 5 times 10, what is the power of this 10? Is 1. 5 times 10 power 1 is equal to 50, okay? So instead of this 50, can you write down 5 times 10 power 1? Yes. 5 times 10 power 1. And what we have in this case? 10 power negative 6. Negative 6 with positive 1, if they have the same base, okay, we have the same base, we can add up the two powers, okay? Bring down this 5 times positive 1 plus negative 6 is equal to negative 5 meter, okay? Both are correct, but we simplified 50 times 10 power negative 6 to 5 times 10 power negative 5. In the case if you have 500, how can you convert 500 to the power? Like this. 500 is equal to what? Is equal to 5 times 100. Okay? So 100 is equal to what? If you convert to the power, it's going to be 10 power 2. Why? Because 10 power 2 is, it means that, or is equal to 10 times 10. 10 times 10 is 100. 5,000 is equal to what? 5 times 1,000. 5,000 convert to the power, it's going to be, how many zeros do you have? 3. 10 power 3. Okay? So this is very important for the students to know how can we convert the number to the power and power to the number. Question 2, guys, look at the question. If the radio wave has a period of 1 microsecond, the period is equal to what? This is question 2. Period is equal to 1 microsecond. What is the wave's period in seconds? So we have to convert this microsecond to what? To second. Which one is larger, second or microsecond? Absolutely, the microsecond is smaller than second. Now we try to convert small to what? To large. Convert small to large, we have to use negative power. What is the negative power of micro? 10 power negative 6. Bring down the given value 1 times 10 power what? Negative 6 seconds. So we cannot simplify this value. Okay, this is the simplest shape for this number. The final answer is 1 times 10 power negative 6 second. We converted microsecond to second. What is the value of micro? Negative 6. Why we use the negative 6 here? Because we converted small to large. Question 3, guys. Look at this question. A hydrogen atom has a diameter of about 10 nanometer. Okay, so question 3, the hydrogen atom, its diameter is equal to what? Is equal to 10 nanometer. Okay, do we have prefix here? Here, yes. What is the type of the prefix here? Nano. Nano is the smallest prefix that we studied, that required for the student to know. Okay, nano is very small. Its power is what? 10 power negative 9. Okay, so express this diameter in meter. So A, convert this 10 nanometer to what? To meter. Okay, now in this case, which one is bigger, nanometer or meter? Meter is bigger than nanometer. This is small to large or large to small? Small to large. Small to large, positive power or negative power? Negative power. What is the negative power of nano? 10 power negative 9. Bring down this 10 times negative power of nano, negative 9, times 10 power negative 9 meter. Okay, so we have 0 here. Can we simplify this? Yes. The 10 is equal to what? This is 10 power 1, but this one is not written here, but already there is a power of 1 above this 10. Okay, times 10 power what? Negative 9 meter. 10 power 1 times 10 power 9 is equal to what? 10 power negative 8 meter. So the diameter after simplified is equal to 10 power negative 8 meter. Or sometimes you can write diameter is equal to 1 times 10 power negative 8. It doesn't matter, okay? It's the same thing. So branch A, we converted nanometer to what? To meter. How many prefixes do we have? Only one prefix. In the case if you have one prefix, it's very easy to convert. Small to large or large to small? Small to large. Positive power or negative power? Negative power. Which type of prefix do we have in this case? Nano. What is the negative power of nano? 10 power negative 9. Okay, so after simplified, 10 times 10 power negative 9 is equal to 10 power negative 8 meter. Branch B, question 3, express this diameter in millimeter. Okay, the diameter was given 10 nanometer. Convert to what? To millimeter. So how many prefixes do we have, guys? We have two prefixes, nano and milli. This double M, what is the first M? Is milli. The second M is meter. Okay, what is our dimensions here in this question? Meter. Okay, because we have many different quantities, and we have three basic dimensions: meter, second, and gram, a kilogram. So gram, sorry. Okay, mass, length, and time. In this case, we have to convert nanometer to millimeter. How many prefixes do we have? We have two prefixes, nano and milli. In the case, if you have two prefixes, convert between two prefixes, you have to solve this question in 2 steps. Okay, in how many steps? In 2 steps. The first steps, you have to convert nanometer to the meter, to the essential unit, and meter to what? To millimeter. Okay, so what is this? This is the essential unit, which is meter. Okay, convert nanometer to meter, meter to millimeter. What is the given value in the question 10? Bring down this 10. Look, this is the given value in the question 10. Convert nanometer to meter, small to large. Negative power. What is the negative power of nano? 10 power 9. multiply 10 power negative 9. And continue. Meter to what? To millimeter. Which one is bigger? Which one is larger? It's very important to know which one is larger, guys. Meter is bigger than millimeter. Why? Because the milli is located below the meter in the table that we studied in the prefixes. Okay? So the prefixes from large to small. A quick reminder to all of you. Giga, mega, kilo, and the unit like meter, second, gram. Okay? After this, centi, milli, micro, nano. Millimeter is smaller than meter. So meter is bigger than millimeter. So in this case, we have to convert large to what? To small. Convert large to small, we have to use positive power. Positive. What is the positive power of milli? 10 power positive 3. So the actual power of the milli is negative 3. But why we use positive? Because we converted large to small. Large to small, you have to use the positive power. Keep in your mind, guys, be careful. And don't forget, convert large to small, we have to use the positive power. So don't care about the negative power for the essential unit of the milli, okay? Times what? 10 power positive. Now multiply. The diameter is equal to, bring down this 10. 10 times negative 9 with positive 3 is equal to 10 power negative 6. 6 is what? What is the last unit? Millimeter. And we can simplify this. It's going to be 10 power 1 times 10 power negative 6 millimeter, which is equal to what? Positive 1. Negative 6 is equal to what? 1 times 10 power negative 5 millimeter. So 10 nanometer is equal to 10 power negative 5 millimeter, yes, but different prefix, okay? So this is very important, and you have to keep in your mind that how can you convert between the prefixes. The last one, branch C, express this diameter 10 nanometer in micrometer. Now we have to convert this 10 nanometer to what? To micrometer. How many prefixes do we have? We have 2 prefixes, like the previous branch, okay? In this case, you have to solve in 2 steps. Nanometer to meter, and meter to what? Micrometer, okay? Nanometer to meter, small to large, 10 power negative 9. And meter to micrometer, this is large to small. Large to what? To small. Why? Because meter is bigger than micrometer. Meter is bigger than or larger than micrometer. So that is why we have to use positive power. What is the positive power of micro? 10 power positive 6. You use 10 power positive 6. But the actual power of micro is negative. Why we use the positive power? Because we converted large to small. In the case of large to small, you have to use the positive power. What is the given value? 10. Bring down this 10. Times nanometer to meter, 10 power negative 9. Times meter to micrometer, 10 power positive 6. Okay? And already we have 10 power 1 here. This is diameter. 1 plus negative 9, negative 8. Negative 8 plus positive 6 is going to be 10 power negative 2 micrometer. Okay? Look, how did we get this number? Once again, look. Bring down the 10. This is the diameter, okay? Diameter is equal to 10 times negative 9 plus positive 6. It's going to be what? Because different sign, 10 power negative 3. Micrometer. Okay? So we can simplify this number. This is 10 power 1. 10 power 1 with 10 power negative 2 is going to be 1 times 10 power negative 2 micrometer. Okay? So this is question 3 about the converting between the prefixes. It's very easy. Just you have to know how can you convert. So at first you have to know that this is which one, large to small or small to large, and also you have to know the power of each prefixes. Question 4. The distance between the sun and earth is about 1.5 times 10 power 11 meter. Question 4. The distance between the Earth and the Sun approximately is equal to 1.5 times 10 power 11 meter. Express this distance with the SI prefix and in kilometer. Okay, we have to convert to what? Kilometer. Okay, guys. How can you convert this prefix to kilometer? We have to convert to what? To kilometer. Meter to kilometer. Meter to what? Kilometer. How can you convert small to large or large to small? Small to large. Why? Because kilometer is bigger than meter. Convert meter to kilometer, it means that small to large. Small to large, positive power or negative power? Small to large, we have to use negative power. What is the negative power of kilo? 10 power negative 3. Bring down the given value. The given value is what? 1.5 times 10 power 11. This is the given value. Times meter to kilometer, 10 power negative 3. Kilometer. It's going to be what? 1 point, bring down 1.5. 10 power 11 times 10 power negative 3 is equal to 10 power positive 9. Okay? So, sorry, 10 power 8. 10 power positive 8 kilometer. Okay? So, in this way, you can convert meter to kilometer, and the distance between the Earth and the Sun is equal to 1.5 times 10 power 8 kilometer, which is equal to what? 1.5 times 10 power 11 meter. Both are correct. The last question, question 5. The average mass of an automobile in the United States is about 1.44 times 10 power 6 grams. Question 5. The mass of the automobile is equal to 1.44 times 10 power what? 10 power 6 gram. What is the quantity or the dimension here? It is mass. Okay? The type of the dimension here is mass because measure it in gram. Okay? Express this mass in kilogram. Convert this gram to what? To kilogram. Which one is larger, gram or kilogram? Kilogram. Gram to kilogram, small to large or large to small? Small to large. Small to large, positive power or negative power? Negative power. Negative power of kilo is what? 10 power negative 3. Bring down the given value. 10 power 6 times 10 power what? Negative 3. How did we get this 10 power negative 3? Because we converted gram to kilogram. The power of kilo is positive 3. But why we use negative 3 here? Because we converted small to large. Okay? So, mass is equal to what? 1.44 times 10 power positive 6 plus times 10 power negative 3 is going to be what? We have to add the powers. 6 plus negative 3 is equal to positive 3 what? Kilogram. Here, kilogram. So if you express this mass into the kilogram, is equal to 1.44 times 10 power 3 kilogram. Okay. So this is the answers of these 5 questions. In practice 1A. Another topic in section 2, guys, in this chapter is about the accuracy and precision. What is accuracy and precision? Its definition is accuracy is a description of how close a measurement is to the correct or accepted value of the quantity measured. Now, I'm going to solve the question about the accuracy and precision. It's very easy. So, like, it's related with the measured value, comparing with the real value, okay? And if the measured values are close to the real value, we can say these measured values are accurate, okay? And precision, what is precision? The degree of exactness of the measurement. Like, for example, if several measurements are made of the length of a book, real length of the book is what? 20 centimeter. What is this 20 centimeter? This is the actual distance or the real length of the book, which is 20 centimeter. And where, like, we have some measurements of this real book, like 20.4, 20.1, 19.8, 20.2, 20.3, 19.6. So, because all the measured value are close to the real value, so that is why we can say that the measurements are accurate, since they are close to the real value. Why these measurements are accurate? Because they are close to the real value. When the measured values are close to the real value, can we say this is accurate? Yes. But for example, if one of the measured value is like 22 or 16, we cannot say this measured value is accurate, because 22 or 16 is too far from the real value. But these measured values are not precise. Why they are not precise? Because they are not very close to each other. So after the decimal, the numbers are not close to each other. Why? Because like 19.6 is far away from 20.4. It is not like a regular and uniform. So that is why we cannot say this is precise. However, another obtained set like measured 21, 21.1, 21.2. So these three measured values are not accurate comparing with the real length. Why? Because 21, 21.1, 21.2 is not close to the real value. So that is why these three measured values are not accurate. We cannot say this is accurate, okay? But they are close to the real, but it is precise. Why? Because they are close to each other. Why this is not accurate? Because they are not close to the real value, but it is precise. Why? Because they are close to each other, and the number after this 21 is increased uniformly, so that is why it is precise. Errors in measurements. The experimental work is never free of error. Okay, for any experimental doing in the physics or chemistry, so there is some error in the experiment. Now we will dive into the how can we reduce this error, and how the people make the error or mistakes during the experiment. Now I'm going to explain in detail. It's important to minimize the error in order to obtain accurate results. Okay, the scientists always they try to minimize what? The error in order to get or obtain accurate results. What are the types of experimental errors? We have two different types of the error, okay? Types of error, okay? How many types of error do we have? We have two types of error. The first one, the human error, and the second one, instrumental error. Okay, in the human error, an error can occur, for example, if a mistake is made in the reading an instrument or recording the results. Sometimes the human make a mistake during the experiment, like reading the measured value, and also sometimes during the recording the measured value, the human make the mistake. So the reading made a mistake in the reading an instrument or recording the results. How can you avoid from the human error? How can you solve this problem, the human error? So to avoid the human error, one way to minimize error from the human oversight or carelessness is to take what? Repeated measurements to be certain they are consistent. Okay, for example, if you try to like measure the distance of the room or TV or anything or table, so you have to make sure that, so you have to repeat your measurements, okay, for make sure that your results and your measurements are consistency, okay? So the repeating is very important to minimize the human error. The second type of the error is instrumental error. Another type of the error is instrument error. If a meter stick or the balance is not in a good condition, like for example, sometimes there is a mistake in the meter stick is not correct, and the balance is not accurate and not correct. Okay, this type of the error is called what? Instrumental error. Like the meter stick or the balance is not in a good working order. This will introduce the error into any measurements made with the device. Okay, how can you avoid? How can you minimize the instrumental error measuring instruments must be chosen very carefully and must be in a good conditions. One of the human error is like the reading measurements, okay? It's called the parallax. What is parallax? Differences in reading the same quantity due to looking from the different angles. Look at this figure. The meter stick is like it's constant, okay? But what is the difference between A, B, and C? For the figure B, the person who is reading this measurement in the figure A is looking perpendicular to the meter stick, okay? Straight or perpendicular. So the best way to measuring like the length of something by a meter stick, so it is very important to reading the meter stick like looking perpendicular to the meter stick, not in the side, okay? Not like this and not like this. You have to look the meter stick perpendicular. Your eyes must be perpendicular to what? To the meter stick. It is not allowed to reading the meter stick in the sides, okay? This phenomenon is called the parallax. If you measure this window by keeping your line slided directly over the measurement like figure A, you will get the correct and the consistent value. You will find that is 165.2 if you look perpendicular. If you don't keep your eye directly above the mark B and C, you may report measurements with the significant errors. Okay? So the parallax is what differences in reading the same quantity due to looking at different angles. This one is wrong and also this one is wrong. Why? Because in this figure B and C, the person who was looking in a different size, not directly perpendicular to the meter stick. But this one is correct. Another topic, guys, is the significant figures. What is the significant figures? Those digits in a measurement that are known with the certainty plus with the first digits that is uncertain. Okay, in the physics and the chemistry, so we have to know the significant figures. In the significant figures, all non-zero numbers are significant. All non-zero numbers are significant. Like, what do you mean by non-zero numbers? Non-zero numbers, it means that number, okay, the integer number without zero, like 1 until infinity, okay? Non-zero, it means that it is not zero. All numbers are significant figures? Yes. All numbers are significant figures, no matter the number is located in the front of the, behind the decimal, in the front of the decimal, okay? It doesn't matter, all numbers are significant. How many significant figures does this number have? 4.352. We have 4 significant figures. Why? Because all numbers are significant figures, no matter the number located out here, okay? How many significant figures this number have? 2.1 times 10 power 3, we have 2 significant figures. Here we have 4, but here we have 2 significant figures. Why? Because 2.1 times 10 power 3 is equal to 2,100. How many numbers do we have? 2. 1, 2. These 2 numbers are significant figures, so that is why we have 2 significant figures in this number. So the significance of zeros varies based on where they are in the number. Okay? All numbers are significant figures. So what about the zeros? Can we say 0 is always considered to be a significant figure? No. We have a problem with the 0, guys. Be careful. 0 sometimes is considered to be a significant figures, and sometimes does not. Now I'm going to explain when does 0 considered to be a significant figures and when does not. We have 4 rules, guys. So you have to keep in your mind this table. It is very important to recognize and to know how many significant figures do we have in the number. Zeros, this table is about the rules for determining whether zeros are significant figures. These 4 rules related with what? With the 0. Okay? Rules for what? For 0. When does 0 be considered to be a significant? Zeros between other non-zero digits are significant. If the 0 located between 2 non-zero digits, or when the 0 located between 2 numbers, this 0 considered to be a significant figure. This is rule number one. Like for example, 2005. 2005 meter, for example. Guys, how many numbers do we have in this number? We have two numbers. These two numbers, significant figures? Yes. Why? Because all non-zero numbers are significant. What is remain? The two zeros. We have a problem with the zeros. When the zero, according to the first rule, this two zero located between the two numbers, yes, so that is why these two zeros also considered to be a significant figures. How many significant figures do we have? 4 significant figures. Why these two zeros considered to be a significant figures? Because located between the numbers. Zeros between numbers considered to be a significant figures. Like 50, another example. Guys, look. 50.3. 50.3 meter, for example. How many numbers do we have in this number? We have 1, 2. These two numbers are significant? Yes. These two numbers are significant. Okay? So what about the 0? No matter we have a decimal or not. Okay? It doesn't matter. This 0 located between the two numbers? Yes. So that is why also this 0 is considered to be a significant figures. How many significance do we have here? We have 3 significant figures. Another example. 3.0025 like seconds. These three numbers are significant. Already we have 3 significant here. Look at the 0. These two zeros located between the numbers, yes, also considered to be a significant. So we have 5 significant figures here. Rule number 2, guys. Rule number 2. Zeros in the front of non-zero digits are not significant. The leading zeros cannot be considered as a significant figures. How? Like for example, 0.892 kilograms. How many numbers do we have? 3. 1, 2, 3. Already we have 3 significant figures. So look at this 0. This 0 is in the front of the numbers? Yes. Or leading 0. Leading 0 in the front of the number cannot be considered as a significant figure. So that is why how many significance do we have? We have 3 significant figures. Another example, 0.008 like milliseconds. Okay? So in this number, how many numbers do we have? 1. So we have 1 significant figure right now. Okay? What about the zeros? This 4 zeros located in the front of the number? Yes. According to the second rule of the 0, 0 in the front of non-zero digits are not significant figures. The leading 0 cannot be considered as a significant figures. These 4 zeros cannot be considered as a significant figures. How many significant do we have? We have only 1 significant figures. Okay? This is the second rule. The third rule, zeros that are at the end of the number and also to the right of the decimal are significant figures. The ending 0 or the 0 located at the end of the number with the right decimal and to the right of the decimal are significant figures. What do I mean by this? For example, 57 point decimal 00. Guys, how many numbers do we have? 2. These 2 numbers are significant. Zeros located at the end of the number with the right decimal, with the right of the decimal are significant? Yes. These zeros located in the front or behind the numbers? Behind the numbers. Okay? If the zeros located behind the numbers with the decimal at the right of the with the decimal of the right, to the right of the decimal, considered to be a significant figures. How many significant figures do we have? We have 4 significant figures. The zeros after this decimal at the end of the number considered to be a significant? Yes. Okay. Another example, like 2.00. Guys, look at this number. How many significant figures do we have? How many numbers do we have? One. This number is significant, okay? Without any rule, because all 1-0 digits are significant. What about the zeros? How many zeros do we have? 6 zeros. This 6 zeros located in the front of the number or behind number? Behind the number. Do we have decimal? Yes. So that is why this 6 zeros considered to be a significant figures. We have 6 zero with one number. It's going to be 7 significant figures. This is the third rule of the zeros of the significant figures. The last rule, rule number 4, zeros at the end of the number but to the left of the decimal are significant if they have been measured or the first estimated digits. Like if we have, guys, the zeros at the end of the number without decimal cannot be considered to significant figures, like 2000. How many significant figures do we have? This 3 zeros located at the end of the number? Yes. Do we have decimal? No. We don't have decimal. If there is no decimal, these 3 zeros are not considered to be a significant figures. We have only one significant. How many significant do we have? One. But in some books, the zeros at the end of the number and without the decimal considered to be a significant figures. But in this book and for the student in grade 10, we have to assume that the zeros at the end of the number without decimal not considered to be as significant figures. Or like, for example, 25,000. How many significance do we have? These two numbers are significant, but these 3 zeros are not. Why? Because we don't have decimal. Do we have decimal? No. These 3 zeros are not significant, so we have 2 significant figures. So that's all about the rules of the zeros, whether it's significant or not significant figures. Significant figures are used to indicate which digits in the measurements are actual and which one are estimated. How many significant figures does this number have? 2.003 times 10 power 7. Guys, don't worry with the power. The power is not a significant figure here, okay? So we have to count only for this number. How many numbers do we have? 2. These 2 numbers considered to be a significant? Yes. What about these 2 zeros? Located between the numbers? Yes. We have 4 significant figures. How many significance do we have? 4. Why these 2 zeros considered to be a significant? Because located between the 2 numbers. Okay? Another example. How many significant figures does this number have? 0.0023 meter. How many significant figures do you have? How many? At first you have to looking for the number. We have 2 number, it means that 2 significant. So what about the zeros? Zeros at the before the number or the leading zero, the zero in the front of the number, considered to be significant? No. Leading zero is not significant figures, guys. How many significance do we have? We have 2 significant figures. This example, 27.000. Look at this example, guys. How many numbers do we have? 2. How many zeros do we have? 3. These 3 zeros between the numbers? No. Leading zero? No. These 3 zeros located behind the numbers and with the decimal? Yes. So considered to be a significant figures. How many significance do we have? 5 significant figures. Okay? So the rules for calculating with the significant figures is very easy. So you studied in grade 8, 9, and also you studied in mathematics. How can you calculate the 2 numbers with the significance, like 97.3 plus 5.85. So we have 0 here and 0 here, 0 plus 5, 5, 3 plus 8, 11, 1 here, 8 plus 5, 13, 3, and 1 here. 1 plus 9, 10 is going to be 103.5. 15. If you round off, it's gonna be 103.2. So the rounding is also very easy, dropping the some digits of the measurement according to the certain rules such that the measurement containing the required number of the significant figures. The numbers, guys, when does the digit becomes round up? Whenever the digit following the last significant figures, like 5, 6, 7, 8, and 9. 5, 6, 7, 8, and 9, it's gonna be what? Round up. It's gonna be what? Round up. But 0, 1, 2, 3, 4, it's gonna be what? Round down. Okay? Find the rounding 42.2 to two significant figures. For how many significant? Two significant. 42.2. Round this number to for how many significant? Two significant. Okay? 42.2. How can you round this number to significant? Indicated, guys. How many significants do we need? Two. Write down this 42. And look at the third number. This 2 is up or down? Up or down? Down. It's gonna be what? Like it's gonna be 0, and we don't write the 0. 42.2. If you're rounding to two significant figures, it's gonna be 42. The final result is what? 42. 42. Find the rounding 3.9, one significant. 3.9 for how many significant? One significant. Okay. We have 3 here, and this 9. 9 is up or down? Up. In the case of up, we have to increase one digit. If you add 1 to the 3, it's gonna be what? 4. 4 is one digit, one significant figure, yes. And 49.81 significant, it's gonna be 50. Why? Because 8 is gonna be up, and this 49 is gonna be 50, and 50 we have one significant figure. Finding round the 42 two significant, we studied 42, okay? And for 3 significant figures, 65.25 is gonna be 65 point what? 3. Why? Because this 5 we have to increase one digit, it's gonna be 65.3. Guys, we finished this section. Now we are going to solve the questions of the section review in this section. Which SI units would you use for the following measurements? Length of swimming pool, SI unit is meter. Mass of the water in the pool, kilogram. The time it takes a swimmer to the swim lap, second. Okay? Express the following measurements are indicated. 6.2 milligram in kilogram. This is prefix. 6.2 milligram to what? Kilogram. Look at question 2, guys. How can you convert 6.2 milligram to kilogram? At first, you have to keep in your mind what is the unit, what is the quantity here is mass. What is this M? Milli. What is this K? Kilo. How many prefixes do we have? 2 prefixes. Because we have 2 prefixes, as I told you, you have to solve this question in 2 steps. In how many steps? 2 steps. Why? Because we have 2 prefixes. At first, convert milligram to the essential unit, and to the gram, and gram to what? To kilogram. So you have to analyze prefix to the basic dimension and basic dimension to another prefix. What is the basic dimension here? Is gram, mass. Milligram to gram, small to large or large to small? Small to large. Small to large, positive power or negative power? Negative power. What is the negative power of milli? 10 power negative 3. Guys, you have to memorize all the required prefixes with the power. Milli, 10 power negative 3. Micro, 10 power negative 6. Nano, 10 power negative 9. After that, convert gram to kilogram. Which one is bigger? Kilogram is bigger than gram. Gram less than kilogram. Small to large. Small to large, still positive power or negative power? It is still negative power. What is the negative power of kilo? 10 power negative 3. Bring down the given value. 6.2 times 10 power negative 3 times 10 power negative 3. It's gonna be what? 6.2 times 10 power negative 3 times 10 power negative 3. It's gonna be 10 power negative 6 kilogram. Don't forget the last unit, guys. Don't forget this kilogram, please. It's gonna be 6.2 times 10 power negative 6 kilogram. The second one, 3 times 10 power negative 9 second in millisecond. B, 3 times 10 power negative 9 second to what? Millisecond. ms. What do you mean by ms? Millisecond. How many prefixes do we have? 1. In the case if we have one prefix, it's very easy. We have to solve in one step. Small to large or large to small. Which one is bigger? Second or millisecond? Second is greater than millisecond. Milli is small, okay? Large to small. Large to small, positive power or negative power? Positive power. What is the positive power of milli? 10 power positive 3. What is the negative power of milli? 10 power negative 3. What is the positive power of micro? 10 power 6. How about the negative power of micro? 10 power negative 6. Why we use 10 power positive 3 here? Because we try to convert large to small. Bring down the given value. Times what? 10 power positive 3 milliseconds. Simplify. 10 power negative 9 and times 10 power positive 3. It's going to be 10 power negative 8 milliseconds. 3 times millisecond, second to millisecond is equal to what? It should be 10 power negative 8. This is 8, not 6. Okay? Sorry. 10 power negative 6. Negative 9 plus positive 3, negative 6. The sign of the larger power, millisecond. This is the final answer. Branch C, 88 kilometer, 88 kilometer, 2 meter. Large to small. Positive power. Bring down 88 times 10 power positive 3 meter. 88 times 10 power 3 meter, or you can make like 8.8 times 10 power what? 10 power 1 times 10 power what? Positive 3. It's gonna be what? 10 power 4 meter. Both are correct, guys. Both are correct. And question 3, this is calculation. It's very easy, not necessary to solve. Question 4, the following students measured the density of a piece of lead 3 times. A piece of lead, how many times measured? 3 times. The density of the lead actually 11.34 gram per centimeter cube. What is the real value of the density of this lead? 11.34 kilogram or gram per centimeter cube. Considering all of these results, which person's results were accurate, which were precise, were any both accurate and precise. So the first one, Rahel, 11.32, measured 11.32, 35, 33. 11.32 is close to the 11.34? Yes. 11.35 still close to the 11.34? Yes. 11.33 close to the 11.34? Yes. So this 3 measured, can you say is these 3 measured values are accurate? Yes, accurate. Why? Because they are close to the real value. Okay? And also, how about the precise? Can you say this is precise? Yes. 32, 33, 35. It is close and repeated uniformly, so that is why both accurate and precise. B, Daniel, 11.43 is close to the 11.34? No. 11.44 close to the 11.33? No. 11.42? No. So this is not accurate. Why? Because these 3 measured values are not close to the real value, but it is precise. Why precise? because after the decimal we have 42, 43, 44. So this increasing is uniform, yes. So that is why it is precise. The last one, 11.55, 11.34, 11.04. This remeasured value not accurate, not precise. Neither accurate nor precise. Okay? Guys, we finished this section 2. Now we are going to explain the section 3 in chapter 1, the last section, the language of physics, mathematics and physics. In this section, we will focus on the language of the physics and the factors that make data easier to understand, and also we will study about the equation, data, and the graphs in the physics and in the other science, and also we will study the dimensional consistency in this case, in these sections. Sorry. What are the four factors? What are the factors that can make data easier to understand? Table, graph, equations. These three factors is very important for doing experiment in physics, chemistry, or any other science. Okay, because we need data, table, and data, graph, and equations. Without data, graph, and equations, we cannot conclude and we cannot get the result, or we cannot doing any experiment. Okay. Once again, listen carefully, guys. How many factors do we have that can make data easier to understand? 3: table, graphs, equations. This is table, guys. Like for example, in the case of following two objects, golf ball and table tennis ball, we need graph to determine like the displacement of each ball and the time taken for following these two objects. We have to make a data, okay? Time, the distance for golf ball, and the distance for the table tennis ball. According to the distance displayed in this table, did the golf ball travel the same distance during every time? No. There is a difference, a little difference between the time, because the distance are increasing with each time interval. What is the Galileo's equation for free fall? This equation is very important, and this is the Galileo's equation for the free fall object, which is equal to 1/2 g(t) squared. In this equation, we can determine the vertical displacement of the falling object and the time taken for the falling object. And also we can we can draw the figures according this table, okay, between time and distance. This figure between what? So this is table, this is equation, and this is graph. Distance and time. If you see this figure, it means this figure tells us that by increasing time, what happened to the displacement also increases. This figure tells us by increasing time, as the time increases, what happened to the vertical displacement also increases. So the equation of the Galileo also can be expressed like this: delta y is equal to 1/2 gravity is constant is equal to what? 9.81 times t squared. Delta y, half times 9.81 is equal to 4.9 t squared. Both are correct. Okay? This is the Galileo's equation, both are correct, but instead of g, we opened and we wrote 4.9. So these abbreviations for the delta y, vertical position, measured in meter, time interval delta t in second, mass in kilogram. Example of Galileo's equation by using the data in table 3.2. Guys, look. When time is equal to 0.2 seconds, when time is what? 0.2 second. When time is 0.2 second, when time is equal to what? 0.2 second. What will be the distance of the goal? It should be 19.6. Now I'm going to prove this number. This is delta y. If time is 0.2, what will be the delta y? Look, according to Galileo's equation, g is what? Constant. According to Galileo's equation, Delta y is equal to what? 1 over 2 times gravity times t squared. Replace. 1 over 2 times 9.81 times 0.2 squared. Delta y is equal to what? Now I'm going to bring calculator. Delta y is equal to 1 over 2, 0.5 times 9.81 times what? 0.2 squared is equal to 0.1962. This is meter, but we have to convert to centimeter. Why? Because the table was given in centimeter, guys. How can you convert meter to centimeter? Large to small, multiply 10 power positive 2. Delta y is equal to 0.1962 times 10 power 2, which is equal to 100, is equal to, I got 19.62 centimeter. Is this the same value of the, I told you 19 point, yeah, I got 19.6. Okay, 6 or 62, it doesn't matter. So this is the power of equation with the data. Now, dimensional consistency is very important. Guys, we have many and we have several equations in the physics. So all the equations in the physics must be consistency. What do I mean by consistency? Now I'm going to prove and I'm going to explain about the dimensional consistency. Like for example, delta y, according to Galileo's equation, is equal to 1 over 2 gt squared. Is this equation correct? How can you determine whether the equation is correct or is not correct? So we have to analyze this equation. If the two sides have the same unit, or if the two sides of the equation, they have the same like dimension, so we can say this equation is correct and this equation is consistency. Delta y, what is the SI unit of delta y? Meter, is equal to 1 over 2 has no unit. Gravity, what is the unit of gravity? Meter per what? Second square. Time, second, time square, second square. Second square with second square cancel. What is remain? Meter is equal to meter. Is this equation consistency? Yes. Or is this equation consistent? Yes. Why? Because they have the same unit. The two sides have the same unit. Meter is the unit for which dimension? Length. Both sides, they have the same dimension? Yes. Both sides, they have the same unit? Yes. Can we say this equation is correct? Yes. Another example, check this equation for dimensional consistency. R is equal to what? Look, R is equal to what? This is the question of chapter review. S minus A, S minus B, S minus C, over what? Over R. R, A, B, C, and S all have units of length. All they have the same units. Okay? Write down the SI unit of R is meter. Meter times meter, sorry, meter minus meter, meter minus meter, meter minus meter. Why? Because all they have the unit of length divided by meter. Okay? Meter minus meter is meter. Why? Because these two variables are not equal. This is not equal to 0. Why m minus m is not equal to 0? Because s is not equal to a. S is not equal to a. S is not equal to b. S is not equal to c. Okay? Like 4 meter minus 2 meter is equal to 2 meter. The result is m. M minus n, it's gonna be m. Times m minus m, still m, m minus m, m. Over what? Over m. M with m cancel. What does remain? Bring down this m. M with m cancel. M times m, it's gonna be m squared. square with the radical cancel. What is remain? M is equal to L. Do they have the same unit? Yes. Same dimension? Yes. Can we say this equation has dimensional consistency? Yes, because they have the same dimension as same unit. Guys, another question. Check this equation. Period. This is period. Measure it in second. This is time. It should be mentioned in the question. This T is period. It's time. What do you mean by this capital T is period? The time taken for one complete cycle is equal to 2 pi L over G. What is the SI unit of period? Second. 2 pi has no unit. L, meter. Gravity, meter per second squared. According math basic, reciprocal for this number, it's gonna be meter times, it's gonna be flip. Second square over L. If you convert this fraction into the multiplication, you have to flip these two numbers according the reciprocal, according math basic, you have to flip these two variables. Meter with meter cancel. What is remain? Second square. Radical square root with square cancel. What is remain? S is equal to S. So it has dimensional consistency. Also, this equation is correct and it has dimensional consistency. So the order of number is very easy. It's not very important. Like this is estimate. The ladybug is 10 power negative 2. The length of your leg is 10 power 0, which is equal to between 0 to 9, from 0.9 meter. Okay, and the length of your school building is about 10 power 2 or 10 power 1. This is estimated. Okay, so this equation, which one is matched? Because the volume increases and mass also increases. When the two variables increases or two quantities increases together, the result will be like this. Okay. So in this case, this equation is matches the data from this item. You can, like for example, pull this number, give the number into the equation. Mass is equal to 1.29 volume. This is mass. If you multiply 1.29 times this number, you will get this number. Okay, you can check it. Determine the units of the quantity described by each of the following. Kilogram times meter per second times 1 over second is equal to what? This is the combination of the unit. It's gonna be what? Kilogram times meter, meter times 1 over what? Second square. It's gonna be kilogram meter per second square. Kilogram times meter, kilogram meter per second times second square, second cube. Kilogram meter per second cube. Kilogram times nominator times nominator, denominator times denominator. Kilogram times meter, kilogram meter. But this square for both square. Over what? Second cube. Okay. Kilogram per second. Look. Kilogram per second. The third one, C, times meter per second square. Open the bracket. This square for mass or for second, for both. Meter square, second square. Nominator times nominator, denominator times denominator. Kilogram times meter square, kilogram meter square. Second times second square, second cube. Kilogram times meter, the last one, kilogram meter. Second times second, second square. Okay, so we finished it, chapter 1, and hope you get benefited from this lesson. Inshallah, I will continue to record the other chapters for the physics for the grade 10. Okay, but the question of the chapter review already is solved here, related with the chapter and with the content that we studied. All questions are very easy. You can solve by yourself. Okay, guys, thanks for listening. Keep up your best doing. Inshallah, in the next lesson, we will explain chapter 2 and the other chapters. Have a good time.